Hey, thanks for the introduction. Thanks for joining us, everyone, today. I'm Brandon Chavis. I'm a solutions architect with Amazon Web Services, and I work in the Amazon Partner Network. Today, we're also joined by Brian Troutwine, who is a senior software engineer at AdRoll, and Matt Williams, who's an evangelist for Datadog. And today, we're going to hear from AdRoll, who leverages the monitoring capabilities of Datadog, which has been built on top of Amazon CloudWatch to help make business and technical decisions. So first, we're going to set the stage, and we're going to give you a quick overview of what CloudWatch is and how it's used. You can use Amazon CloudWatch to gain system-wide visibility into resource utilization, application performance, and operational health. You can use these insights to react and keep your application running smoothly. For example, you can monitor the CPU usage and disk reads and writes of your Amazon Elastic Compute Cloud instances, and use this data to determine whether you should launch additional instances to handle the increased load. CloudWatch comes with hundreds of free metrics across AWS services. It's automatically enabled, and there's no setup required. However, it does have a lot of customizable alarms, notifications, and automatic actions you can take depending on what you might be running on AWS. It can monitor your services, and you can publish your own metrics for systems and applications. CloudWatch allows you to monitor metrics on Amazon DynamoDB tables, Amazon EBS volumes, RDS database instances, Amazon Elastic MapReduce job flows, Elastic load balancers, SQS queues, SNS topics, and more. CloudWatch fits in with CloudTrail and SNS to monitor API actions, log files, or your application responses, and take action based on your specific requirements. CloudWatch enables many flexible and diverse use cases. So, for example, you could create an alert that emails your finance department when your EC2 costs exceed a certain value for the month. Or perhaps it could monitor and alert you when your IAM configuration changes. Or it can track read replica lag on your MySQL RDS instances. Or it could monitor the amount of failed jobs in your Elastic MapReduce cluster. Each service has a unique list of dimensions and metrics that are particular to that specific service, so the permutations of resource monitoring are exponential. We're going to dig in a bit specifically on CloudWatch Logs right now. And CloudWatch Logs can be used to monitor your log files for specific phrases, values, or patterns. CloudWatch Logs differs a little bit from standard CloudWatch because instead of being a service-level monitoring utility, like monitoring EC2 instance CPU utilization or DynamoDB table latency, logs are usually an OS or a system-level construct. Because of this, CloudWatch Logs comes with an agent, which is just a piece of software that runs on Linux or Windows and handles the communication with the CloudWatch service, and it ships your logs off for storage and monitoring. This agent is configurable via a simple config file, and it allows you to specify things like which files to monitor, your log format, and the length of time to retain the log. Once the logs are shipped off, they're stored up in the CloudWatch Logs service, and then you can use the CloudWatch Logs console to build monitoring and filters and trigger certain alerts if specific conditions arise. So real quick, let's look through setting up an alert. So this is the Amazon CloudWatch Logs console, and this is what you would see if you hadn't set anything up before. And there is a quick start guide you can use. You can also see on the right-hand side here, there's the option to install the agent via CloudFormation or Chef, or to install it directly on an EC2 instance. So in CloudWatch Logs, you have an option to create a log group. And here we're going to look at an aggregation of all the var log secure log files from our instances in EC2. So inside the log group, we can see the log streams from specific instances. Here we have one instance. If there were multiple instances, we would see log streams for each instance. If you click on the log stream, you can see what's actually in the log file. And here's all the specific entries in that log file in var log secure. So going back here, we can create a metric filter, which will search through this var log secure file for that particular instance and alert us when something has happened. So what do we want to look for? Let's add a metric filter, and let's look at what filter pattern we want to actually extract from this log file. So here you can actually specify your filter and test the pattern against the logs in CloudWatch Logs to see if it actually captures what you're looking for. So there are some examples you can use here. Some of our suggestions are error, info, warning, and you can also do things like look for timestamps, requests, specific users. Basically, any pattern you think you can match, we should be able to support that. So right now, we're going to look for error. We can test this, or invalid user right now, but we can test this and see how many results actually show up in this log file. So here we found one match. So we're going to go ahead and create this filter and assign a metric. We have to create a namespace. So we're going to call it var log secure. We're going to look for invalid users because we want to know if there's been invalid login attempts. We're going to move forward and create that filter. After that filter is created, you can then create an alarm and define a threshold for when it should alert you. So we're going to call it the invalid user login. We're going to define how many consecutive periods does this need to actually occur for us to be alerted. And then we're going to define the action that we're going to take. In this case, we're going to use an SNS topic to notify us. And SNS can alert you via SMS, email, or it can publish an HTTP action to an HTTP server for you to take an action on as you see fit. So after the login, or after the invalid user login alarm has been created, we can see here what's been happening and if it's an alarm, and if there have been alarms kind of on a historical basis here. So to wrap up CloudWatch Logs, that was a quick walkthrough, but how is this useful? Well, really it's a granular view into your resources, into your application and OS level logging, and it uses the same powerful alerting logic that comes with standard CloudWatch. So leveraging these capabilities in conjunction with AWS service level monitoring allows you to really stay in tune with the state of your full application stack. So everything down to application level logs all the way up to the big picture with EC2 instance health. It's also useful for things like change management, auditing, and long-term storage of log files. So here's our call to action here. Take a look at CloudWatch today. It has a really generous free tier, so you can take a look at what you can do to improve visibility into your infrastructure with CloudWatch for free. Chances are there's already metrics for all of your resources that you're using in AWS right now. Take a look and see what's been going on, and you might find some really valuable information in there. So at this point, we're going to pass the baton to Datadog to talk about how they can help you leverage CloudWatch for your monitoring needs.
Awesome. All right, so my name's Matt Williams, and I'm the Evangelist here at Datadog. And Datadog's a SaaS-based monitoring platform that makes it incredibly easy to understand and monitor the health of all of your servers, both physical and in the cloud. Now, monitoring is incredibly important, and we work hard to make that process as easy as possible. If you don't monitor, you don't know if you're maintaining your level of performance. Performance could be increasing because of a change you made in the right direction, or worse, you might have made what seemed like a minor change and performance is decreasing. Running experiments relies purely on subjective comparisons rather than real, actionable data if you're not monitoring. So to start monitoring with Datadog, you ideally add a simple agent to each host you wish to monitor, and then we start collecting immediately. Now, I say ideally because there are actually options to use proxy machines and monitor remotely, but it's best if you install everywhere. And with a fairly standard Chef or Puppet or Ansible or SaltStack environment, that's pretty trivial. So now every second we record the current value for each metric, and soon we can start showing you the data that we collect in some pretty interesting ways. Now, since you're listening to an AWS webinar, you're probably already using CloudWatch. And for those metrics, we don't need an agent, and we can start collecting at whatever interval you've got configured in the AWS console. But when you combine the CloudWatch metrics with the metrics collected by the agent, you get a much more complete view of your environment with 1 second granularity. For instance, we can show you a dashboard. Now here we're looking at Sabatka. Sabatka isn't a single server, and it's not a single application. Instead, it's one of our internal roles made up of about 80 or so EC2 instances, which are made up of applications like Redis and CookieBouncer and Console and Nginx and many other things. So here in this dashboard, we can see information on throughput, connections in Nginx, CPU utilization, memory usage, and the size of various types of payloads that Sabatka deals with. Now, on their own, each metric from each host tells a really tiny piece of the story, and this might be what you've been able to work with before. But when we aggregate all the hosts together, we get a much more complete picture of the environment, and we can see how Sabatka is performing rather than just how a specific instance is doing. Oh, and if that name sounds kind of familiar to you, you're probably as familiar with the TV show The Wire as we are. You look around our environment, and many of the characters from that show seem to come to life. So when you zoom out to see more than just a few minutes, we can start to see the patterns in the environment. If there's a daily pattern, we can identify it here. Weekly and monthly patterns start to pop out as well. Our ops and dev teams can see what's going on now and work together to improve it. We can identify patterns and look for trends as the service grows. We learn from views like this that would be pretty much impossible with any other tool. And you notice that these graphs are looking at all of the 80 or so instances aggregated together, and I've zoomed out to see about 10 months of data all at once. So to make it as easy as possible to get a complete view of your environment, we've worked really hard to build about 100 different integrations with the applications you already use. Things like GitHub or Postgres or Mongo or Cassandra or Chef or Couch. There's just so many more. Now, most of these integrations can be configured and collecting data in a matter of minutes. It simply requires uncommenting a few lines in a YAML file and specifying an endpoint where we can collect the data. And in most cases, the default settings that we provide you are exactly what you want. But for this webinar, we're specifically talking about the Amazon Web Services integrations. And the AWS integrations are set up using your access key ID and your secret access key. You know, those two really long numbers that used for various applications. So then you can enable or disable the other AWS integrations that you want to use. So in this case, I could enable or disable MapReduce or EC2 or DynamoDB or Route 53 or so on. Then we start collecting all of your CloudWatch metrics at your subscribed update level. As soon as you start, depending on the individual services enabled, we start collecting a huge amount of info. Without a way to manage and sift through all of these metrics, monitoring all of these instances could potentially get very difficult. If we just look at EC2 metrics, we have about 13 points of information that get collected, including, well, what's here? CPU credit balance, CPU utilization, disk read ops, disk write ops, host OK, and so forth. There's a bunch of other ones for ELD and Redshift and SQS and others. But when you start collecting a few dozen metrics related to AWS, plus you add on a few hundred metrics from the specific applications that you're using, and you do that for every instance, you quickly get into the thousands of metrics to monitor. Doing this effectively is pretty hard to do. So at Datadog, we've chosen to use tags to help you organize and find the metrics you collect. With tags, you can find the answers to the questions you have about your environment quickly and easily. Now on this slide, I've put together a few examples of tags you're probably already familiar with. up at the top left is a part of my mailbox on Gmail. For one message, I've assigned tags, or what Google actually calls are labels. And the labels I've chosen are dev and support. Now I can find the message in the list of all emails for dev or for support. Below that, I have the Finder window in OS X. And here I'm looking at the Gmail screenshots in my Dropbox folder, and I've assigned the tags Datadog Demo and Gmail. Then over on the right side, I have my AWS console showing several of the tags that get automatically created, like name, as well as a custom tag we created at Datadog for demos, and I assigned it a value of MacDemo. So if we can start assigning tags to metrics, we can create queries like this. Let's say we want to monitor all Docker containers running image web in region US West 2 across all AZs, and make sure that resident set size is less than 1 gigabyte on C3XLs. Well, I can convert that to using tags where image is a tag with a value of web. Region tag has a value of US West 2. AZ has a value of all. And instance size has a value of C3XL. So once I've created these tags, it's pretty easy to change the query using the same tags, but this time looking for containers that use more than 1.5 times the average resident set size. Now, the reason this is difficult without tags is that containers have lifetimes of minutes or hours, rather than the days or weeks or more that instances might have. So over the course of a month, we might have hundreds or thousands of instance names. Managing them by name is going to be very difficult and time-consuming. But with tags, the job becomes so much easier. So once you start using tags and collecting metrics from all of your applications, you can start doing some pretty interesting things. You can create alerts based on metrics for entire roles across your environment. You can create alerts that affect a percentage of all the machines within a specific role. So earlier I mentioned Sabatka, and Sabatka happens to be made up of 80 different instances on AWS. I can create an alert that only alerts me if 50% of the instances have one specific problem. You could also create dashboards, like the one you saw at the beginning of this segment. Now, some of these graphs show individual lines for each host or all the lines are kind of stacked up on top of each other. Some of the graphs show an average. And then there's one that shows a heat map, so you can quickly identify the average values along with all the other outliers. But graphs alone only show a portion of the picture. They show you what you thought was important at the time you created the dashboard. As you learn more, which you will, about the environment, you find other metrics and other events that add context to the graphs. Here we're looking at AWS events that occurred at the same time as the two graphs on the dashboard. And then we can hover over each event and watch the graphs to get a better idea of what happened when. I didn't know when I created this dashboard that the AWS or EC2 events would be interesting. It's only at view time or at analysis time that I realized, I wonder how those relate. And maybe I change this after I look at EC2. Maybe I look at Jenkins deploys or GitHub commits. And I look at all of these different types of information overlaid on top of the graphs that I created a while back. So all of these tools are available to help you get a better understanding of your environment. So to see how a real customer has applied this, let's actually hand it off to Brian Troutwine from AdRoll.
All right. Hello, everyone. So I am Brian Troutwine. I'm a senior software engineer at AdRoll, and I primarily work on the real-time bidding system. What I'm hoping to do here is take you through the increasing arc of sophistication. So in my time at AdRoll, when I started, when we were using the real-time bidding system, we were not very sophisticated in our understanding of how to monitor it, and ultimately in our understanding of the system itself. To give you a little background on what real-time bidding is, it is an advertising technique for a concept called retargeting. So if you are an advertiser, if you do old-style advertising, you hand over a big chunk of money to a magazine and hope that the people that see your ad are the right people. Retargeting uses information about the people that are going to see the ads to target the ads so that they're more likely to be interested in the ad. The problem domain for real-time bidding is interesting in that it has these constraints. Each bid, because it occurs on the web, has to be low latency enough, 1/10 of a second, so that users don't notice that there isn't an ad when your page starts to load. So you have about 1/10 of a second to figure out how to price a bid, which is what the system that I work on does, and what ad to show, all sorts of things to optimize, to retarget. It's what's called a firm real-time system. So for those of you who don't know the sort of jargony definition of real-time, it means that there's an implicit clock to the computation, and your computation does not have value if it goes past that deadline. Hard real-time system means that something disastrous has happened. Firm real-time means that your computation just doesn't have any value. The real-time bidding system is highly concurrent, meaning that at peak we do approximately 2 million transactions a second. We do several billion transactions a day, and all of these are done in 1/10 of a second with this sort of hard deadline. And the system is global, and it never shuts down. In fact, it can't shut down. It's designed not to. And these particular constraints, even though they're simple to say, made for a very interesting experience as we sort of scaled our ambitions. So in the early days of the AdRoll RTB project, we could sort of use our intuition about how to deal with the system. You know, when we would discuss changes to make, we had a fairly accurate mental model of what would happen through the changes that we would make, mostly just because the system itself was simple. There were relatively few parts. And we can sort of explore their interactions in our minds. And we had a small total number of requests at that time. I think maybe 10 million in a day. So, you know, in effect, nothing. And the impact of mistakes were few. So at that time, when we could still rely on our intuition, if we went offline for a few minutes, it was, you know, tens of dollars lost, a relatively low impact. We could be reasonably confident that our mental model of the system's behavior was accurate. We could sort of sit down together and think real hard and have a decent chance of figuring out what was going to happen. But as we scaled up our ambition, the trouble with a complex system is its behavior gets away from you pretty fast. You start finding yourself in situations where you can't reason through all the interactions, or you make a small change and it has an outsized impact. So we recognized that we needed to have some sort of empirical process in place, because we're all engineers, we're all failed scientists in one way or another, but we sort of hold on to the scientific method. So our first approach was to batch process the logs that came out of the bidders. The bidders generate a significant amount of system logs. The advantage of this is that we were already doing it. We feed our data science team with these logs. So we have a high reliability way of transmitting these logs to another team. And it's simple to implement. Like, I'm sure many people in the audience can already imagine how they would do this and how they would make sure that the logs are delivered. And it's relatively straightforward to conceive. It's not that much of a jump to say, hey, all of these machines that are generating logs, we should use those logs. The problem that we have with batch processing logs is that they have a high update latency. In our case, we're taking these logs, and when we go through the data science pipeline, we push all that information into Hadoop. Hadoop is a batch processor, so it has a job that runs periodically, and that period is relatively high. If we have any sort of catastrophic errors in AWS, we lose the logs if the instance is unable to transmit those logs to the secure storage. And the fact that it's so high latency and it takes messing around with Hadoop to figure out what's going on in the system, it denies impulse experimentation. So it denies your ability to say, I have an idea, let me try it out. So that approach, while better than nothing, while better than sitting around and thinking real hard, was not ideal. So our second approach was to generate coarse real-time metrics and try and analyze those. So what I mean by coarse real-time metrics is we had relatively few metrics coming out of the system. They had relatively long periods, meaning we would get about one metric a minute, but they were real time, so we could get some sense of how the system was behaving in practice. And the advantage here over batch processing is that it's just an iterative step. It's simple to move from batch processing, which is on the period of, say, an hour, to something that's on the period of, say, a minute. And it proved out the concept for us. It demonstrated to us that it was useful to have real-time monitoring and instrumentation of the system. And it was also simple to implement. And the advantage of it being simple to implement is this system, as we're sort of going through this process of figuring out how it works in practice, was becoming more and more core to the AdRoll business. The cons, unfortunately, is that you still have to rely quite a bit on intuition. You have to be able to take this stream of coarse data and apply it to some sort of model that you have in your mind and make sense of it. The problem there is you sort of hit confirmation bias. You sort of hit this case where all of the engineers believe that the system should be behaving in a certain way, so they warp the evidence to that hope, that bias. And the bidder implementation was suboptimal. It caused performance degradation at high loads. And the partner company that we were using to build the dashboards out of this coarse real-time data, the dashboards were a one-size-fits-all deal. You would sit down and you would spend quite a bit of time putting them together, and then if they didn't sort of fit your mental model, if they were difficult for you to understand, that was too bad. This is before we were using Datadog, incidentally. So, you know, this approach was better, but it still had defects. And by this point, the complexity of our system was growing very rapidly, and the business's ambitions for it were growing, which is a good place to be in, but it's also kind of a tricky place to be in. So we added 2 engineers to the team. So we effectively doubled the size of the team. AdRoll whole was growing very, very rapidly. So we had tens more in the department. We're now up to 100 engineers or so. And as we added more engineers, that added more pressure on the bidding system because many of these engineers were data scientists or they needed information for their own projects. And as a result, the RTB project became one of the central projects of AdRoll. So it's this very high priority team. And because of the place that we were in for our monitoring and our instrumentation, we were making decisions, very important decisions in a knowledge way. We had no way of really saying, you know, this is a good idea or this is a bad idea. At this point, we had CloudWatch. So CloudWatch is great. It's effectively free relative to our other AWS costs. Finance never comes and knocks on our door about CloudWatch. And CloudWatch is the basic health of your system. So at AdRoll, we're extensive users of Amazon Web Services. And CloudWatch gives us the basic health of our instances, but it's also the total view of the AWS systems that we're using. So, you know, it tells us how DynamoDB is doing. It tells us how RDS is doing. It tells us how our load balancers, which is hugely important for us, are doing. But what we don't have at this point is a detailed view of the real-time bidder system. We have no way of saying, except in this very coarse manner, which is polluted by confirmation bias, how the bidders are doing, how different features that we've integrated have affected the system. And what we don't have, especially, is the ability to explore the information we have in high-stress situations. So if something has gone wrong, or we've hit a system fault in the bidders, we have no ability to sort of throw things together and form hypotheses and then figure out how to resolve the problem, or even better, figure out how to never hit that problem again. So we started looking very seriously at resolving this, at getting more fine-grained real-time metrics out of the bidder system, getting quick and easy dashboarding, quick and easy alerting, and getting instrumentation in the bidder that is a high-performance system that wouldn't degrade the performance of the bidder itself. So at AdRoll, we're an airline shop. We use airline for all of our high critical systems. And there's a wonderful library called Exometer. So if you happen to be an airline user and you need instrumentation, I highly recommend Exometer. I've talked about it in, all last year I talked about it. I've traveled around. So it makes collection of detailed application level instrumentation both cheap and easy, which has just been a game changer. And Datadog solves our aggregation, visualization, and alerting problems. So our need to take all of these, metrics coming out of all of our instances and turn them into something sensible visually and then set alarm thresholds on them so that we can react has been hugely valuable. And everyone in our team has their own set of dashboards. So we're all working on the same project, but we all have our own different models about how it should work, and we all have our different visual biases. And that's been hugely useful for us to all have our own set of dashboards. So Datadog integrates with CloudWatch, so we can take these metrics that Amazon provides us about the systems that we rely on, and we can correlate them to our application-specific systems. And this can be done in real time. And real time will be on a second latency, which is hugely advantageous when we start making finicky little changes in configuration, which I'll discuss in a bit. And this can be done in high-stress situations. So when everyone is very concerned about what's going on, it's easy for us to sort of figure out what's going on and how to resolve it or who to contact. And the thing that we didn't anticipate is that Datadog is so easy to use that non-engineers can use it. We have people from business intelligence or finance or marketing. They come to us and they sort of point to dashboards and they say, what does this mean? So other people are getting intuition about this very important system that is at sort of the core of the AdRoll business. And the first couple of times that happened, that just blew my mind. So now I want to walk you through three different examples on our arc of sophistication as we started getting these fine-grained real-time metrics aggregated through Datadog. And you'll see that we start out not very sophisticated, and then by the end, we're making elaborate decisions based entirely on the instrumentation. So a bit of terminology first. A bid, which is one of these things we have to submit in tenths of a second, we say that it times out when we don't reply back to the exchange or people like Google or Facebook, the people that own the ad slots. We say that it times out when it doesn't get back to them in 100 milliseconds. So after and timeouts are hugely important. If we time out too much, our traffic gets throttled. And if our traffic is throttled, we are not able to spend money for our customers. So that it's a crisis moment. So after we had instituted this sort of regime of fine-grained monitoring, what we found out when we looked at timeouts were that we had these periodic massive spikes. I don't know if those of you on the webinar can see on the left-hand column there, but we go from effectively 0 to, at peak, 4,800 timeouts, instantaneous. And this happens pretty regularly. You can see a pretty decent pattern there. And in fact, we didn't realize this was happening. We had no idea this was going on. And it was an early win of our sophisticated monitoring. It was something that surprised all of us. So being relatively new to this, we started building dashboards and we started forming hypotheses. And we looked at the system load. So we looked at system CPU. And this is the same time span as the timeout spike graph, and you don't really see any giant jumps in CPU. So there's nothing really correlated there. The CPU load is normal, and there's not really a periodic spike in bid request traffic either. And we can look at that because of the CloudWatch metrics that we get from AWS. We can see the amount of bytes in and out. And here, interestingly, we do, though, see that we have this peak in bytes out. which is surprising because we don't really have a peak in bytes in. So we started asking ourselves, what does that mean that we have this correlation in network traffic? And so we started diving deeper, and we used our understanding of how the Erlang virtual machine works, and we looked at what's called the run queue. So it's a bit of inside baseball with regard to Erlang, but Erlang is able to support its massive concurrency by having these things called run queues. And the Erlang virtual machine is itself very finely instrumented, and you can see how many processes there are, green threads backed up, waiting to be run. So what you see here is process spikes in the Erlang virtual machine, and these are correlated with the timeout spikes. So we had our culprit, but we had to sort of ask ourselves what was going on. And it turns out that it was a configuration problem with the way we had our boxes set up. So the Erlang virtual machine scheduler, we locked their threads to CPUs. And we had a CPU-intensive background task that would kick on every 20 minutes. So the problem there is we had no CPU shield set up on the server, so the virtual machine scheduler thread got kicked from its assigned CPU. And when it got kicked, all of the processes that it had queued up, they got dropped for a little bit, and then they all time out because we're on this firm clock. So that was one of the very, very early things we discovered, and it sort of proved out very quickly that this sort of detailed monitoring both solved our conceptual limitations and had real tangible business value. So the next one was something that plagued us early on while we were still trying to figure things out. We would have traffic crashes, and traffic crashes, bid request traffic crashes, they're an all-hands problem. Everyone drops what they're doing, or did drop what they were doing, and looks into it. Without traffic, the bidders can do nothing. They have no purpose without traffic. So this is an example of good traffic patterns. This is over multiple days, and you can see this sort of diurnal curve as people wake up and go to sleep. And many of you who do auto-scaling will be familiar with this sort of curve. And you see it's cross-region. So each one of these colors here represents a different region of the Earth. And these, by the way, are all Datadog graphs. Our use of Datadog is so ingrained with the way that we do things, I have no idea how else I would display this information. So these are a healthy couple of days worth of traffic. It's the night and it climbs in the day, and it's fantastic. This, on the other hand, is a crash. This is a great cliff of despair. You see on the left-hand side, we had a relatively normal amount of traffic, and then bam, we hit this sort of trough where the exchange is sort of testing us out to figure out if we can handle traffic. The problem is that's a weekend worth of traffic loss. This is very early on in our instrumentation. We hadn't yet figured out how to do alerting. So we all rolled into the office on Monday morning and were very surprised by what we found. So we confirmed with CloudWatch that the networking to the machines was fine. We could receive traffic in and out. The standard background traffic had not been interrupted on the weekend, so that wasn't the problem. No changes have been made to the production system on Friday afternoon either. This is also a looser time in the bidding team, and sometimes that would happen. And all of the detail metrics from the VM are acceptable. So the run queues aren't backed up. We've not exhausted any internal resource to the VM. Everything looks good. And so we go basically we have no idea what's going on. So we go to our partner and we confirm with them that the traffic has crashed. But what we don't see is spikes and errors on their side. Anything that they would normally do to throttle our traffic, we don't see something that would cause that. But we have at least confirmed a drop of traffic from their system. So it's not actually us that has failed to load traffic. Maybe there's an ELB problem. None of that. We are ready to go. They're just not sending us the traffic. So that's progress. And so through our monitoring, we sort of discovered that we had this problem, but monitoring didn't really tell us what the problem was. So we had to reach out to our business partners. And it turns out we actually triggered a bug, an implicit limit, to be kind about it, in their implementation. We synced over too many cookies, greater than 2 billion, and they assumed that would be fraudulent. It turns out it's not fraudulent. We have greater than 2 billion cookies to sync to them, but because we tripped that limit, they throttled our traffic. So this was a really great example of alerting being very valuable. If we had discovered this on Friday afternoon at 2 p.m. when it started, we could have contacted our partner and had this resolved before the weekend. So we became much more conscious at this point about rolling out new features and discussing how to monitor it. So this is the first point at which all of our engineering discussions became centered around the idea of how would you monitor this? How would you instrument this so that you can alert on it in case it goes wrong? And the last example that I have is what we call the CookieBouncer. So this is an example of us having the sophisticated ability to say how things behave in real time because we've become good at this sort of engineering. So for those of you that don't know, there's an incredible amount of fraud in the online advertising industry. Just mind-boggling amounts of it. And that is something that we've had to become sophisticated at dealing with here at AdRoll. And a certain kind of fraud that we've identified, we call the hot cookie. The problem with the hot cookie is that it triggered a fault, a tolerable fault in the bidders. It caused us to overload our DynamoDB tables. And the solution for that is something that I'm currently working on now, but when we identified the problem, it was something that was going to be a few months out. So we needed an interim solution. So you can actually see through our CloudWatch metrics that these are our DynamoDB user profile throttling. We're getting our request throttled because we're requesting too much information. So as an interim solution, we decided to build the CookieBouncer. So it blocks bidding on fraudulent so-called hot cookies in real time. These are cookies that appear too frequently. They're clearly not human. No human is capable of sort of doing what these hot cookies do. But our concern was blocking too much legitimate traffic. So what we needed to do was be able to instrument the behavior of the CookieBouncer, deploy it in a very conservative fashion, and then sort of fiddle with the numbers so that we could figure out a good level to have the CookieBouncer set to. So we built a new CookieBouncer dashboard. The people that were working on this project, we all sat down and we built one dashboard so we would have the ability to tune it in real time on every bidder and sort of discuss amongst ourselves and build these experiments. So we rolled CookieBouncer out with very conservative settings, and we started adjusting, keeping tabs on the sort of key indicators for the health of the bidder system. So we would crank the CookieBouncer level up, we would wait about 30 seconds, we would see the change in Datadog, and then we would evaluate and ask amongst ourselves if we felt comfortable with where we were. So this is an example of the wins of the sort of CookieBouncer. So this is one of the key metrics from the bidder system. We are always very concerned with how well we're winning. And you can sort of see as we're playing with the CookieBouncer here that there's not that much of a shift. So we're not destroying quality traffic. But as we adjusted, we were very surprised at the total number of blocked cookies and the percentage of total traffic. So as we crank the numbers up, from very conservative to a little less, but still very conservative, we see that the sort of rate of cookie bounce just climbs very, very drastically. So on this particular exchange, or on particular exchanges, I should say, there's a fair bit of traffic that is just fraud. And the total number of cookies that we sort of blacklisted, you can see us experiment and reset off on the left-hand side. You'll see growth, and then we freak out and we reset it, and we turn it back on again, and we see the same level of growth. So we convince ourselves that that's normal behavior, and then there's a dip again where we reset it and we set it back up with a more stringent level, and we see this sort of slow growth of bounced cookies. And we sort of kept asking ourselves, is this too much? Are we blocking legitimate traffic? But the instrumentation speaks for itself. And one of the key metrics now in the bidder system is what we call the prediction, the idea that the person that we bid on will click or do something that our advertisers want. And we chart that too. And so this is what happened after we enabled the CookieBouncer. The prediction rate just shot up. because we just dropped fraudulent traffic. And this was one of the most impressive episodes to date of us using this sort of real-time monitoring and instrumentation combined with sort of key CloudWatch metrics to drive real business value for AdRoll. And this we just did in an afternoon, and it's been tremendous. So that's it for me. Thank you, everyone. I see we do have some questions, so I suppose we'll get to that. Let's see. The one question that I'll tackle is Brian mentioned Erlang. Do I need to be an Erlang developer to use Datadog? And the answer to that is no, absolutely not. We use Erlang because we need a high-performance real-time system that is programmable by mere mortals, but Datadog is not, emphatically not Erlang specific. It's cross-language. You just install it and you go. In AdRoll, people use it from Python, from Java, from Go, from C++, just from every language you can imagine. Let's see. I'll just keep jumping in unless someone else wants to answer a question.
I can take a shot here. There's a question about streaming logs from Journal D into CloudWatch Logs. And that's interesting. I don't know specifically, but I would encourage you to take a look and see if there's like a connector for syslog. So for example, it's easy for, if you're aggregating log files with syslog, you can push log files into CloudWatch Logs using syslog. And we have some documentation on that. And I think I can follow up afterwards if that's easier and we can talk about this. But just due to my lack of familiarity with Journal D specifically, I don't know exactly how you would get it into CloudWatch Logs. But if there's any sort of connector, again, with syslog, there might be something to look at. So I'll follow up with you after the webinar, and we'll talk about that more. Interesting question. Thank you.
There's a question here, how many metrics do you collect? I'm not sure if that question is aimed at me specifically, but I can answer it. We collect from the bidder system, just from the bidder system, our application-specific metrics are in the thousands, and I can't even tell you how many come through CloudWatch. We rely on several hundred, and then we sort of have different priority levels for the metrics that we collect. Some are what we call key metrics. They're the key health of the system. Others are useful for diagnosis in the event of a crisis.
And I'll build on to that answer. If the question is more about how many metrics do we collect across all of our integrations, then, well, we have about 100, I think the number is about 101, 102 integrations at the moment. And some of those, we collect just a few metrics. Some of them are like AWS, where we've got about 60 or 70 metrics. Others, like Elastic, formerly known as Elasticsearch, was around 100 or so metrics. So the number really varies. Now, if the question is actually about, well, how many metrics from all our customers do we bring in, well, then the number's in the billions per hour. So we bring in a lot of metrics, and we're dealing with a lot of stuff. So different ways of answering that question.
We're hearing some cheering on the line. I got a question. How exactly do you use CloudWatch metrics? And follow up, can you please compare CloudWatch to other event collection systems? So CloudWatch we use at AdRoll, at least in the bidder team, and I can't speak for other teams very, very accurately. In the bidder team, we use CloudWatch mediated through Datadog. So we rely on Datadog to collect everything CloudWatch related so that we can correlate CloudWatch metrics to our application-specific metrics. So the application-specific metrics are foremost because they're the ones that are tailored to our needs. And then we use the more general metrics to figure out what's going on or to determine auto-scale events, things like that, to test. How does Datadog handle and show Shield CPU instant graph? The thing is, we don't actually really at this point concern ourselves all that much with CPU. The only place where we concern ourselves with the CPU is when we know for auto-scaling. When we go above 90% utilization, we scale the cluster up a little bit. Can you actually speak to that? When you use a CPU shield, how does Datadog deal with that?
Sorry, I don't quite understand the question.
Okay.
What's the
So
question?
are you familiar with CPU shielding on a Linux system?
I'm not, no.
Oh, okay. So to explain for those of you that aren't, Linux has the capability of saying that there's a certain application is solely given control of system CPUs. So what we do in the bidder system is we give the bidder all but one system CPU, which is why we're not really all that interested in CPU metrics anymore, except for auto-scaling. I believe that Datadog only shows the CPU that it is assigned to. So, but CloudWatch metrics show total system CPU. So I don't believe that CloudWatch is aware of CPU shielding.
Yeah, and I don't know if Datadog is specifically aware of shielding.
Yeah, Datadog we have isolated on the one system CPU, so Datadog wouldn't be aware of the other CPUs in the system.
Yep. One of the other questions, I'm not sure if it was already addressed because I kept falling off the line, was what type of runbook automation is available? Was that question already addressed?
No, it wasn't.
So I'm not exactly sure what the question is asking. I think so the full question is, what type of runbook automation is available to Datadog and AWS? For example, if my RDS instance is pegged on CPU, I might need to get data from the DB quickly to diagnose it before it goes away. So I think the question is about, can we, based on something happening, can we do something automatically to get more data? And we're not able to respond to activities. When something happens, we can send an alert out, but we're not able to go and collect more information, maybe information from the database. We're just going to keep collecting all the information that we've been configured to collect. So I'm not sure if that's the answer, if that's where the question is going, but it's about the best I can answer for that one. What else have we not answered? Are there any others that we missed?
One question was, have you considered calling this event CookieBouncer? We already have another event called CookieBouncer. We have a lot of Sesame Street puns. Let's see. I think we may have gotten everything.
Yeah. Maybe open it up for the last few questions from anyone anyone who's listening. If you have any questions, ask. We'll try to get to them.
There is a question. How long are metrics stored for in Datadog, and what granularity are they stored in as metrics get older? We did miss that one.
Okay, so the answer to that is we keep all those metrics for a year. And, as metrics get older, we don't, average them down to every 5 seconds or 10 seconds. We keep them at 1 second granularity for the entire year. So 1 year, and we don't change anything.
We actually use that quite a bit when we need to compare the behavior of the system over a long period of time, especially if we've made something that we consider to be a radical change. It's very, very useful to be able to make that correlation. And on the win graph that I showed, those different lines are actually wins current over day, over week, over month. The graphing API that the dashboards provide is pretty complete. see. What is the maximum metrics that so this is in my private Q&A. What is the maximum metrics Datadog can track? Assume all collecting metrics data flow in concurrently.
What's the max? What was the question again?
So I think what's being asked is how many metrics can you collect concurrently?
We haven't hit a limit yet.
Yeah, we haven't swamped you yet either.
No. Hey, you send us a lot of stuff.
Yeah, we kind of abuse you guys. Thanks for that.
No problem. Keep it coming.
We will.
All right, so I think we have no more questions, correct?
Yeah, I believe we've covered everything.
All right, thank you very much, everyone, for joining our webinar for today. This will conclude our webinar for today.